Hello viewers, welcome to Physics with Sanmitra. I am Sanmitra Bhomik and today we are learning the part 2 of the spring force lecture, and today I will be teaching you what will happen if we combine two springs of say K1 and K2 spring constants into series and parallel. So let's begin. Suppose we have a spring that is having spring constant K1, and we have another spring that is having spring constant K2. What will happen if I connect them in series? Let's say I am connecting them in series. What will happen? I am applying a force F, and say this part it is at a support. Now what will happen? Now let's draw the free body diagram of both the springs. Here is one spring, here is other spring. This is K1, this is K2, and I am applying a force F. See, ultimately after application of force X, after both the strings, see this one will be elongated by x1 and this one will be elongated by say x2. After both the springs get elongated by their respective elongations, the whole system will be at equilibrium. So this spring is not moving anywhere. After being elongated, it will remain at equilibrium. So the equal and opposite force will be acting here in the backward direction, so that this F and this F will cancel. This F and this F will cancel. Then only this spring will be at equilibrium. Now here also, since this F is acting here, definitely this force will also be F and this force will also be F. So in case of series combination, since the springs after elongation are not, the springs are not moving with any acceleration, they are at equilibrium, so all the force will be F. This is F, because this spring is not moving, and since these are action reaction pairs, so this is also F, this is also F. It is acting like tension, and this is also F. Now this is x1, this is x2, and let's assume the contraction of the two spring system, that is x. Now we can say this x is equal to x1 plus x2, because see, this spring is getting displaced by x1 and this is getting displaced by x2. Definitely both together will be displacing x is equal to x1 plus x2. This is simple addition. Now x is equal to x1 plus x2. Now what I can say, what is x1? X1 is F by K1. X1 is F by K1. And what is x2? X2 is F by K2. What is x? X is the same force F by the total displacement, that is the effective spring constant, say that is K. So I can cancel F, I can write 1 by K is equal to 1 by K1 plus 1 by K2. This is my effective spring constant in case of series connection. So that will be the reciprocal summation of individual, the reciprocal of the equivalent spring constant will be the reciprocal summation of the reciprocals of inverse of spring constants of different springs. Okay. Now let's look for parallel connection. What do you mean by parallel connection of spring? This is one spring, this is other spring. Both are connected at one support, and say both are being pulled by a single force, that is F. This is K1 and this is K2. Now can you tell me what is the effective spring constant? Just see, when I am pulling it by a force F, what is happening? Let's draw the free body diagram separately for both the springs. This is spring 1, this is spring 2, this is K1, this is K2. See, here there is no need for the forces to be same. I mean, this is F1, this force is F1, and this force is F2, because definitely it will not be same, it may not be same, so I'm assuming it F1 and F2, and but these springs are at equilibrium after getting extended by say x1 and x2 or something, or the required elongations. It will be F1 and this will be F2. Now, but what is the constraint? Achha, both will be same, here also both will be same, but what is the constraint that both the string will move together? That is, see, the one end, both ends of the string, or the spring, sorry, the spring are connected at common ends. So I can say the elongation in both the spring will be same. X, that is same for both the spring. Otherwise, one spring will elongate more, other will elongate less. That is not the case. Both will elongate by the same distance, because this support and this support, say that, let's say this is A and this is B. This A is common for both and this B is common for both. Simple. But what we can say is that this F at equilibrium, this spring is exerting force F1, this is exerting force F2. So I can say these two will be equal to F. See, this F will be countered by this one by exerting F1, and this is exerting F2. This F is equal to, I can say this F is equal to F1 plus F2. F is equal to F1 plus F2, and the next line we can write the total, let's assume that the spring constant is K. K into X is equal to K1 into X, F1 is K1 into X, plus K2 into X. So K1, if I cancel out X, is equal to, if I cancel out X, now K1 is equal to, sorry, K is equal to K1 plus K2. So in case of parallel spring constant, it will be simply the summation of individual spring constants. So we have learnt about spring combination in series and in parallel. Now let's see this problem. We have a block of mass m, and we have one spring here, we have other spring here, and say this spring constant is K1, say this spring constant is K2. This is the surface. Now I am displacing this block by a displacement x on the right hand side. I am displacing this block by a displacement x on the left hand side. Can you tell me the net force on this block? Find the net force on block. This is the question. Now, first of all, tell me one thing. These two springs are in series or parallel? Just pause the video for 1 second and just tell me it is series or parallel. Okay, I think you have thought about it. There will be many of you who will say it is series, and there will be many of you who will say it is parallel. Now the correct option is not series, it's parallel. Now you will say, well, how it is possible? These two are in the same line and connected, so this should be in series. But no, this is not in series, this is in parallel. Let me explain how. Just see one thing, what used to happen in the parallel connection. In the parallel connection, if you remember, the displacement of two blocks was same because both ends were connected at common points. When I am displacing this block by a distance x on the right hand side, these two springs are constrained in such a manner that the elongation in this spring is x and the compression in this spring is also x. The elongation in the spring with spring constant K1 is x. This is x. But the compression in the spring with spring constant K2 is x. So what will happen? This K1 will pull it with a force K1 into x. This K2 will push it with a force K2 into x. So net force on the block will be K1 into x plus K2 into x. That is K1 plus K2 plus K2 into x. K1 plus K2 into x. That is our, I can say, the effective spring constant for both the. Now you might be thinking why it is so. Why did it happen like that? See one thing. Just I am explaining in short. These two sections of the spring, these two parts of the spring, they are connected with on the block, and these two parts of the spring, the end parts, they are connected on the support, fixed support. So we can say that this is the common point is the block, and these two are the support. Since it's a different support, one spring is experiencing compression, the other is experiencing elongation. Had both of them in the same block, then both of them would have together experienced compression or elongation simultaneously. I hope you have understood this topic. Now if you like our video, then please subscribe our channel and please share this video with your friends. And I hope you are learning well from our videos. So please practice the problems, and we will be uploading some good quality problems in Newton's laws of motions and the topics we have covered so far. So stay tuned for the problem series.